our computer is stored in binary, right? Everything is zeros and ones. So reason being that the smallest components that we have seen is the logic gates, and since we use electronic circuit, so it's easy to just store things in just binary numbers. So it's the zeros and one as off and on, right? As because of logic gates or our little circuits can just do like 0 volts or the 3.3, the minimum, or the 5 volts right now. So you have zeros and ones on and off, which is simple enough to be like doing the logical operations on it. It's the same as doing the Boolean algebra, which is the true and false, right? So we would assume that everything we see is a discrete number. So in this, right now, in this level, it's gonna be like zeros and ones, zeros and one only. So true and false, zeros and ones. So the Boolean algebra is one of the logical, it's a algebra that operates on the only this true and false binary numbers. It's named after George Boole. He said that we can use any logical operations on these true false things. So we can use and, or, not, XOR, NAND, NOR. It's just like multiplication or the addition. And then, so we can have simple operations and derive logic. Okay, so the simplest one is the NOT gate. So the NOT gate has only one input and one output. So it will just operates only on one bit. What it does is very simple. It's just reverse the value from 0 to 1 and 1 to 0. So it has the symbol of the triangle with the NOT at the end. So if you have just triangle, it will go out as just the same. Input and output is the same, right? So we use the circle as a symbol that is NOT. And here is the truth table for the NOT gate. So truth table is just displaying input and output. So we have all the possibilities of the inputs. Input can be zeros and one. And then we say, if the input is 0, what's the output? Okay, so this would be a simple truth table of a NOT gate. Anything comes back, rings a bell of the Boolean algebra before? It's true, false, same thing, zeros and ones. So from NOT gates, we have AND gate. AND gate has two inputs, A and B. What it does is they AND them together or multiply them together. But here in logic design, we use AND. And AND is that if the output will be true only if both input is true, right? So basically, both input has to be ones, and then the output will be one. So we can write a truth table out of it. It's that input is AB. If any input is 0, then the output will be 0. If both of them is 1, then it will be 1. So we usually write it as a dot, little dot, like a multiplication, right? Or some people use and if you're lazy, then sometimes you would just use nothing. So like A, B means A and B. Okay. And or is that any of them? Okay. Any of them is 1, the output will be 1. So The only case that is not going to be 1 is that none of them is 1. So if input is 0, 0, output will be 0. Other than that, if any of them is 1, so A or B is 1, then output is 1, right? So we use a plus or the addition sign for it. So A plus B means A or B. And it's a bit of a more complicated symbol. So XOR. XOR is that it has to be different, then it will become 1. So if it's the same, it will be 0. So A and B, 0, 0, the same, it come out 0. And then if they're different, so it's 0 and 1 or 1 or 0. So different, inputs are different, then it will come out 1. This is XOR gate. So the symbol is the plus with a circle around it. And then there's a NAND and NOR, which is a not AND and a not OR, right? So it's the opposite of AND and OR. So what we have is AND gate, and then we invert it at the end. So we draw just the AND gate here, and then we invert it at the end with a bubble. So it means like the output will be the same as doing the AND. So AND has to be both 1 is true, right? So both 1 is true. So if you just AND this, it will be 0, 0, 1. And then you invert it, so it will become the opposite. So it's 1, 1, 1, 0 here. So it means that both input has to be 1, then the output will be 0. Okay. So the not AND, so it's the opposite of AND, right? And not OR is the opposite of OR. So it's like, if any of them is 1, the output is 0. Otherwise, it will be 1. So, of course, you can just remember AND and OR, and then remember that not AND is just the opposite of that, and not OR is the opposite of that. So when you write it down as a not, to say that, so not, you can use a negate on the top, like this, right? With a bar on the top, or some people will use the, like, we would use this sometimes in the mathematical form, okay? Or when we type, usually we're lazy, so we use just the exclamation mark and A sometimes, right? But when you write it down on the exam or on the paper, it's easy to just write the bar, and you can see clearly that this is not A, okay? So they all correct, just that if you have a long thing, then it's not easy to, like this one, it's not easy to see which exclamation mark is for, right? So if you write A, B bar like this, it's clear that both of this is A and B, and then all of them bar. So not A and B. And or, since it has a space, it has a plus between it, so you write it as have a little parenthesis to make it easier to see, and then have the bar. So this is not OR. So NAND and NOR are very convenient. So we can build any logic gates out of NANDs and NORs. It's easier to build a physical circuit, but that's the details of lower level. It's easier to build the circuit from into NAND and NORs, than ANDs and ORs. So it's more beneficial to design the circuit into NAND and NOR form. But you don't have to worry about that, because we have, at this point, we have all the tools to change it for you. But just so you know, you can build any logic gates out of NAND. Like for the NOT, if you want the NOT A, instead of using a NOT gate, you can just put A NAND with the A, then it will become, so since not A is that if A is 0, then you want A to become 1, right? Not A. And then, but then you put the A connect to each other, then it means that if A is 0, both of this is 0, it will come out as 1, right? Because A and 0 is 1. It's 0 and you not it, so it's equals to 1. So 0 and 0 is 1 is 0, and then you not it at the end, so it becomes 1. So you can build a NOT gate out of just A NAND A, and you can build an AND gate as well. If you want to do A and B, then you can just do A NAND B and then NAND A NAND B. So you have to just write it down in truth table form. That if you have AB 0, 0, 0, 1, and then 1, 0, and 1, 1, what is the output of this 1 by 1? Or you can write it in the Boolean algebra format. Is that A NAND B, means like this. And then you NAND with the A NAND B, and you do this. So with the Dermogan's laws, remember, you break the bar into the parentheses, it will change the operation into AB bar or AB bar. Dermogan's law is that if you have to limit it. So if you want to put the negate into the parentheses, then you have to change the operators change. Okay? So same here. So it's A bar, B bar, B bar, or B bar, and then same thing here. You can build the NAND gates. We can build the OR gate out of NANDs. Okay? Let's say that is that most of the gates that we use now will be just in the form of NANDs and ORs. So here's the Dermogan's law, is that if you want to break the negates into the parentheses, you have to change from multiplication, which is AND, to OR the same goes as from OR to AND. So with the basic gates that we have, it's just AND OR, XOR, NOT, NAND, and NOR. We can build any logical functions or arithmetic functions, like what we have learned in the ALU parts, in the CPU parts. So let's say if you want to build something based on the condition. So like if you have a S and A, B, if you want to say like, let's build a circuit that has a selector S. If S is equals to 0, you have to let A out. Sorry. And if S is equal to 1, you have to let B out. Okay. So we can draw a truth table out of it. So basically you have a circuit and then you have A, B, and then S. Right. You want to do the circuit that simple that say that if S is equals to 0, you have to put the input A out to the output. And then if S is 1, you want to have B out to the output. So you have that kind of a rules set, and then you can start designing the circuit by doing the truth table. So the truth table will be, you have 3 inputs, right? A, B, and S. and then you have one output. So if S is equals to 0, from the example, if S is equal to 0, then you let A out. So you see if S is equal to 0, then you have A out, so you put A. So here, A is 0, so you put A here is 0. So when you do the truth table, you just write the outputs. This one is A. So S is 1, let B out. Here B is 0, so B is 0, so output is 0. So same goes here. If S is 0, have B A out here, so 0. And then if S is 1, B is 1, so have B out here. Same to the bottom part. S is 0, let A out, so it's 1. S is 1, have B out, so it's 0. And S is 0, have A out, so it's 1. S is 1, have B here, so it's 1. So we have a truth table of a simple circuit that if S is 0, let A out, and if S is 1, let B out. So we have, from truth table, we say that we write down the equation of the output. It means that the output is going to be 1 when. So when we write the equation, we say output is going to be 1 when this block here is that when A and B and S is 0, 1, 1. So if A is 0, you write all of these and together. So it has A has to be 0, so A bar. And B has to be 1, so and B. And then S has to be 1, so and with S. Okay, this is the first one. Or the second one is that same thing. A, B, S has to be 1, 0, 0, so it has to be A, B bar, S bar, right? So good so far. You remember this the whole thing? Okay. So from truth table, you can derive the logic from that. Okay. In this third case, is that 1, 1, 0. So it has to be A, B, and S bar. So yeah. After some time, you will omit it all. Just write it down together. So the last case is that ABS. So here we have the output circuit from the truth table as an equation. You can simplify the Boolean equations by using the Boolean algebra law, like identity law, 0 and 1 laws. So I just sum it up here. So from this equation, you can try to simplify it using the law. So basically, if you see something that you can make the equation shorter, you can reduce the size of the circuit. Like this, for example, you see that the common thing that you can pull out from the equation would be like the S or S bar, A or B, A or B or something like that. So like here you see like, okay, we have S here, and then S bar here. So you do like S outside, and then the inside would be A bar B. Or with this one, or with this one, is that AB here. And then you, for the second one, you have the S bar outside, and you have A B bar or AB here. Anyway, so you can simplify it simpler and simpler using all these laws here, and then you have a smaller circuit at the end. Okay. Okay. So this is just to show you that no, these days you don't have to do it by hand anymore. So you have like hardware description language to reduce the size for you. You have all the other method like the K-map, using the Kano map to do the simplify the logic function for you. So like this case, you have the K-map, and it's the using the inputs A, B, and S, and write the output inside the table, right? And then you can simplify it as well. So like this, it's like you circle the 1 1s, and then you get the VS, or this 1 1 here. It's just another method here is that you see where the number 1 output is from. So here, 1 1 here has to be VS here, and this one here has to be A. A has to be 1 here, and then S has to be 0 here. Okay. So it's the same output as doing the Boolean algebra. You get the most simplest form by using both methods. The selector that we just did, it's the circuit, is that it's called a multiplexer. It's a common circuit that we use everywhere. It has the name of mux and the number, 2 numbers, which is the inputs and then the output. From that one, it means you have 2 inputs, A and B, and then you have one selector, and then you select 1 output out. So it's the number of inputs to the number of outputs. It's like if you have 4 to 1 multiplexer, it means that you have a number 4 inputs, and then you have a selector. So if you want to select 4 inputs, you have to have a selector of 2 bits. But we're not gonna write it down here. It's just called the inputs and outputs that select 1. So the selector has to have 2 bits here. If selector has 1, it means that you have B out. If selector is 2, it means that you have C out. Okay. So selectors select which input you want to take it to the output. So from that, what we wrote is A, B, and S, right? So it's similar thing here. So we derive the circuit out of it. So it's that A and S bar, right? And B or ES, right? So here we have A, B as a box. Okay, so if you don't want to write the detail of the gates inside, you just write as a box with the inputs and then output. Okay. And then the detail inside, it would be A and S bar. So instead of writing the NOT gate, you just do the bubble instead. Okay, so here is A S bar, or with using this OR gate here to combine the 2 output of these 2 ANDs here. So this is BS, right? So AS bar or BS will come out as the output. So another arithmetic circuit that we did before in ALU is the adder. So adder is just adding 2 1-bits together. So you have A and B, you just add them together. And then the output here is R. So since you have 2 digits, right? 2 binaries, right? You add 0 and 0, you get 0. You add 0 and 1, you get 1, right? 1, 0, we also get 1. But then if you add 1 and 1 together, then you have 1, 0, right? Because it's binary number, it's just like decimal numbers that if you have out of numbers, like you're gonna have to carry to the next bit, right? It's just like you add 9 and 1, the output will be 0 with the carry of 1, right? So the same thing here is that you add 1 and 1, you have output as 0, and then you get a carry over to the next bit. Okay? So when you add 2 bits together like this, so you're not gonna have just one output, you're gonna have output as is here as sum, and then you're gonna have a carry out as well. So the truth table will have 2 inputs and then 2 outputs. So, and then when we look at the output, so sum is that if the inputs are different, then the output is 1. So it's the same as XOR gate, right? So output can be written as A XOR B. Is that if A and B are different, then the output is 1. And then the carry is that you only get 1 when the 2 of them are 1s, right? So your carry is A and B. So this circuit is called a half adder. Okay? Half adder has 2 inputs A, B, and 2 outputs. If you want to have more than 1 bits adding together, just like when you add the numbers, you're not gonna have just 1 bit, 1 digit, right? So you have to have a carry from the previous bit as well. Just like when you add 9 and 11, right? You're gonna have to have this bit, you have just 2 inputs, right? 9 and 1, you get 0, and then you get a carry of 1, but this one you have to add this digit, which is 0 here, and then 1 here, and then you also have to add the carry here, right? 1. So you actually, if you want to add 2 numbers together, you actually have to have 3 inputs. So you have A, B, and then carry in. Okay. So you can make a full adder from 2 half adders. You can build a 1 full adder, but you have 3 inputs and 2 outputs instead. Same here. You want to have a circuit with 3 inputs, you write the truth table for all the possibilities. So 2 to the 3 is 8. So we have 8 possibilities. You have truth table of 8 possibilities. So it's from 0, 0, 0 to 1, 1, 1. Right? This thing can switch in place, doesn't matter, right? You can have A, B, and C, or C and A, B, whatever. And then you have the outputs of 2. So it's the summation and the carryouts. So same here, you write the equation from where it is 1. So like the R, the summary, is that when this 1 is here and here. So you can just write it straight from the truth table that's saying like it's 1 when CAB is 0, 0, 1 here, right? So R equals to 1 when C is 0, A is 0, and then B is 1. This is the first one. Or is the 0, 1, 0. 0, 1, 0 is C, A, B bar. Or it's 1, 0, 0. So it's C, A bar, B bar here. Or all of them is 1. So CAB. So here we have the circuit of summation. So the R is equals to this. And then the same goes with the carry out. Carry out is 1 here and here. So you see carry out So C out is 1 where it's 0, 1, 1. So 0, 1, 1. So C bar A, B, or this 101, 110, and 111, right? 4 cases that you can have 1 output. So this is just how to, if you just use a 2 half adder, so you have A, B here, and then you get the outputs, and then you add the carry in later. So you can just use 2 half as well. So, but it's just adding 2 at a time. So add A and B first, and then add the carry in later. And then so you get the carry out, and then the summation. So the carry out here is that if both carry is, if either carry is 1, then it come out 1. Okay. How to write the block diagram out of it. So you have 3 inputs, and then you have 2 output, and hiding whatever inside. You have to show it. So you're just saying that how many inputs are there, how many outputs are there. So this is a combinational logic, is that you have the output that change according to the inputs. Okay. Simple, the easy ones. Okay. So whenever input change, the output change. This is a combination circuit. So you can have truth table, and then you write out the circuits.